If you're running a reverse caching proxy like Varnish in front of your website to speed up slow pages or to make it more battle-proof when you have lots of visitors, you probably want to know how it performs. Is the page that was served a hit? Did it come from cache? Or was it a miss? Was it served from the backend? And if it was a miss, why is this the case? What happened behind the scenes? Well, luckily there's a tool that is called Varnishlog that comes with the standard Varnish installation, and that gives you that insight, that view behind the scenes. And this video is going to show you how it works and how you can operate Varnishlog. However, it's important to know that Varnishlog is just a binary and a utility that wraps around the Varnish Shared Memory Log, or the VSL. VSL is a piece of memory where a running Varnish instance stores its logging information into. It's transient, 81 megabytes in size, and you can have a look at what's currently happening. It's not persisted in a way. It doesn't give you historical information by default, but it gives you a clear insight about what's currently happening and where you're currently at in the flow of the Varnish finite state machine. Let's give you a bit of a taste and show you an extract of some Varnishlog output. I'd like to stress that this is just an extract. The full log is way more verbose and has lots more information, but this shows you a little bit how it works. You see a transaction here, a request transaction, with some information that might or might not be relevant to you. You see that there's a bunch of tags. These tags are named, in this case, begin, timestamp, rec start, rec method, rec URL, rec protocol, and rec header. And these have values next to them that should give you a bit more meaning. But before we dive into this, I should explain to you how transactions work. Every time you access the Varnish Shared Memory Log, transactions are sent to the output along with their corresponding log lines. These transactions are the actual items of work within VSL, and for that matter, the Varnishlog binary. Transactions are identified by transaction IDs, or VXIDs as we call them, and there's two kinds of transactions. On the one hand, you have sessions, on the other hand, you have requests. Sessions represent HTTP connections that are made from the clients to Varnish. If you have keep alive on your server, multiple requests will be sent through a single session. And that's also something we'll notice throughout this video, that the session can hold multiple requests. Requests, on the other hand, are either incoming requests from the client to the server, backend requests from Varnish to the backend server, or sub-requests, ESI sub-requests that are sent from Varnish to the backend server. Let's visualize this concept by showing you the following image, courtesy of Varnish software. What is actually happening there is a series of events. It's a chain of events that is executed by a single incoming request. That incoming request triggers a session, that session triggers the actual request, and that request, because it was not stored, or the response was not stored in cache, triggers a backend request. The output only displays individual transaction information and the begin tag of every transaction that was filtered out. The begin tag shows you what kind of transaction we're dealing with. Then it is followed by the transaction ID of its parent transaction, followed by the reason why this is currently happening. So let's have a look. What happens first is a backend request followed by the actual request, followed by the session. So the order of execution is off, but that's due to, first of all, encapsulation and hierarchy, but otherwise lack of transaction grouping. All these transactions are displayed on the same level, but the last stage is displayed first, again due to encapsulation. And you can see that clearly at the right-hand side of the image. You see that the backend request that is identified by transaction ID 3 is the innermost transaction, followed by the actual request, which is identified by VXID 2. And finally, you have VXID 1, which represents the session that is displayed then. There is some meta information. The transactions themselves have their own VXID, 3, 2, and 1, and the begin tag refers to its parent VXID. So you could see that the backend request depends on ID 2, which is the request. The request depends on VXID 1, the session. And the session itself has 0 as its parent transaction ID because it really doesn't depend on anything. In the previous example, you noticed that these transactions have a relationship with one another, but it wasn't really made that visual. It wasn't visually clear. The only way you could determine that one transaction depends on another one was by using the begin tag and determining what the parent ID was. But using transaction grouping mechanisms in Varnish, it could be made much clearer. And in this section, we'll show you the different kinds of transaction grouping and we'll apply them to a single example. Varnishlog offers 4 transaction grouping mechanisms. By default, all the output and all the transactions are grouped by VXID, but we can also group by session, by request, or raw. And we'll apply them to a single example of content composition that you might know. Header, footer, navigation, and main page. And by running through these examples, you'll clearly see the different kinds of transaction grouping. Now, what is particular about this example is that there's not a single resource that is requested to display the page. In fact, there's 4 resources that need to be addressed. You have the main resource, the home page, that is represented by the main frame on the right-hand side. You have the footer that is called by a separate AJAX call. And then we have the header and the navigation, and those are edge site includes, or ESI calls. ESI calls are placeholders that are marked in your source code, and Varnish is clever enough to read those, determine what the source is, and do a subsequent request to the backend, and group the output as a single page. Well, let's get to it. What you're currently seeing is the very first execution in this video of the Varnishlog binary. What you'll also see is we're not adding any grouping mechanism, so we're using the standard grouping mechanism, VXID, but there is an addition there. You see the -i parameter with tags like begin, rec URL, link, and brec URL. This is a bit of a spoiler. There are ways in Varnishlog to filter the output by tags, and this is how we'll do that. Of course, we'll dive a lot deeper throughout this video, but the first thing we'll be doing is filtering the tags and only display the begin tag, which we've seen so far, the request URL tag, the link tag, and the backend request URL tag. And this is the output. This is what we're currently seeing. Because of the standard grouping mechanism, we're seeing one of the innermost transactions first. We're seeing the backend request that was sent to the home page. Next to that, we're seeing the backend request that is made to the header by the ESI call. What we're seeing then is the actual sub request within Varnish for that header, which is also an ESI call. What's up next is the backend request for the navigation, followed by the ESI sub request for the navigation. Next up, we're seeing the actual request, and using the link tags, we can see the subsequent requests that follow this main request. So although we're requesting the home page, there's different kinds of transactions that need to follow. A backend request transaction to fetch the main data. And when that data gets parsed, it will notice that there's 2 ESI tags. So there will be 2 ESI sub requests, which we've already seen and which trigger a backend request themselves. What follows next is a separate backend request for the footer that is initiated by the next request, the actual footer request. And these 2 transactions are wrapped into the session. That means the main request and the AJAX call to the footer request. But let's show you a bit more hierarchy there by displaying the following image. So what you see is that a session is enabled, 2 requests are set, a main request and a request to the footer, and each of these have 1 or more resources to be called. The main request triggers a backend request and 2 sub requests to the header and to the navigation. The header and the navigation on their turn do a backend request for their resource, for header and navigation. And then finally, the footer just has to trigger a backend request to retrieve footer information. I hope that makes it a lot clearer. So you see that there's a hierarchy between these requests and their links. Thanks to the begin tag, you can see what it depends on, and thanks to the link tag, you can see what it triggers next. Let's improve this situation and apply a different kind of transaction grouping. You have the very same command, filtering on the very same tags, but we're going to add -g session. So we're going to group by session and have subordinate transactions indented. And you see that by the asterisk. The session has a single asterisk, the request has 2 asterisks, and then the next one, the footer request, also has 2 asterisks. What you see next is the backend request for the homepage has 3 asterisks, so it's an extra level of indentation. Next up, you see the very same thing for the header. The header is a level 3 transaction, and it goes all the way up to level 4 when the header has to be retrieved from the backend. So the header is already a sub request that depends on the main request, which depends on its turn on the session, and it has to go all the way down. Session, request, ESI sub request, ESI backend request. You'll agree that grouping by session instead of VXID makes the visual representation a lot more comprehensible. We can also do the same thing and replace -g session with -g request, and then we'll be grouping by request. The output will look similar, the only difference is that we'll omit session information. And when we do -g raw, every single line will have its own transaction information. Correlation is completely lost, but that has its own use cases. As a Varnishlog user, it is your primary objective to figure out where you're currently at in the flow, where do you transition from, and where you're transitioning to. This requires a good understanding of the finite state machine that Varnish offered with its different stages. It is visualized here right in this image. There's a lot more information about the VCL flow and the default behavior on the Varnish documentation page, but also written about it in my Varnish book. Have a look at it right here. There's a link to the blog post where you'll see it and where you'll find information about my book that explains VCL behavior. VCL behavior in Varnishlog is actually expressed by the different tags that are grouped in certain transactions. So transactions or types of transactions give meaning, but these different tags do as well. And the decision-making process is pretty straightforward. You get a request incoming and you analyze if it's cacheable or not cacheable. If it's not cacheable, you'll pass it to the backend. The backend will fetch it and return it to the end user. If the request is cacheable, a hash is composed out of the URL and the host name, and it will be looked up in the cache. That can either trigger a hit, the hit will return an object and will deliver it straight to the end user without communicating with the backend. If it wasn't found in cache, it will trigger a miss. The miss will trigger a fetch, a backend fetch. The backend fetch will result in a backend response, which will in its turn be delivered to the end user. And that's actually the flow. That's actually how it works. Now let's go over the different tags that are linked to these different stages. Let's kick this one off by showing you the different kinds of request tags. As you can see here in the example, the output displays the rec start tag, which indicates the start of the request, and captures the host name and the port of the server that initiated it. So in this case, it was a local host connection over port 56312. This is followed by information about the request itself. The request method is get in this case. It could be post or put or delete or anything else. And then you see the actual resource that is addressed. In this case, this is the home page, the slash page. Next up is the protocol that is used. In this case, this is HTTP version 1.1. And then you see a sequence of request headers. You see a host header, localhost, a connection header, we're keeping it alive, so that means that multiple requests will be sent through the same session. Then we have some other stuff like upgrade and secure requests. We see the user agent that was addressed, what capabilities the client has in terms of accept, so we can access text HTML or XHTML and so on and so forth. We also can deal with encoding, gzip, deflate, BR, and the language that my clients can support is either Dutch or English. And then finally, we see that there's an X-forwarded header on the local host, which displays the node that was set in front of Varnish. In HTTP, you have requests and responses. We already dealt with requests. Let's have a look at responses. The output you're getting is tailored around the concept of HTTP response information. You have the protocol, in this case 1.1, the status, which signifies the status code. This is a regular piece of output, so the status code will be 200. The reason for that status code is also mentioned. It's okay. And then you have a sequence of response headers that were returned by the backend. A host header, cache control information, date information, an E tag, cache variations, the length of the content, the type of the content, a custom X Varnish header that was inserted by Varnish that displays the VXID of this transaction, and also a custom one, the age, which signifies the amount of seconds that an item has been stored in cache. When an item can't be retrieved from cache, a backend connection needs to be made, and information about that backend is also displayed in Varnishlog. You see that there's a backend open and a backend close tag. The backend open tag gives you information about how a backend was determined and which VCL was used. So in this case, you see that boot.default was used. So that means we're using the boot VCL, and within the boot VCL, there's a backend named default. Default represents a connection to the local host on port 8080, and the connection originates also from localhost from port 62552. The backend open is numbered, it has ID 19. We can close that backend by linking to it. We say backend close on 19, and what we're actually closing is a connection to boot default. So the boot VCL default backend. When Varnish interacts with backends, it will have to send backend requests and retrieve backend responses. We can use the original request and the original response object for that, but Varnish decides not to do that and has intermediary objects. It uses a backend request object and a backend response object. And these tags can also be displayed in Varnishlog. And as a spoiler, they're very, very similar to the original request and response tags. So let's have a look. We can have backend request method, backend request URL, backend request protocol, backend request header. Sounds familiar, right? Well, same deal for responses. Backend response protocol, backend response status, backend response reason, and backend response headers. There's even a third form here, which is objects, and that's the way these items are stored in cache. So these store the object protocol, object status, object reason, and object headers. And now we have the full circle of request and response storage tags. But as explained, it is our primary target to visualize transitions within the Varnish flow. And the objects that we have, request response, backend request, backend response, the actual object, gives us meaning about what's stored and what is transmitted. But transmission happens based on a state change, and that state change is easily displayed via VCL tags. You'll have VCL call and VCL return tags that are quite important, but you also have VCL error tags and VCL ACL tags. Now the ones I use most are VCL return and VCL call, because they tell you what VCL stage was called and what transition was made to the next one. Let's have a look. So in this example, we're only displaying request transactions, so there's no session information here, and we're only displaying the URL that was called and the VCL call and returns that were made. So what you can determine from request 5 is that a request is made to the home page, the request is received within the receive stage, it was deemed cacheable, so we're performing a hash. So we're doing VCL return hash and going to the VCL hashing stage. In that VCL hash stage, a lookup is made. We've looked it up in cache, but unfortunately, it was not found in cache. So it's a miss. A miss needs to be fetched. And when we fetched it, we'll deliver it back to the end user. Now, it is important to know that the fetch triggers another request, a backend request, and that is identified in that same example by transaction number 6, the backend request. The backend request triggers a backend request URL, and it results in a backend fetch. That backend fetch fetches the information, and we're going to the next stage. Once we fetch the data, we're going to backend response, and the backend response will deliver the information back. That's useful information. There you can see what stages are executed, and that helps you along with the decision-making process. Let's try another example where a backend fetch isn't made and a hit is returned. Let's do it. Backend request 6, it calls the home page. The receiving logic is triggered. It returns a hash because it was deemed cacheable. That hash was looked up and it was found. It results in a hit. That hit that returns the object that was stored in cache is immediately delivered back to the user by sending it to the deliver stage, and in the deliver stage, it is sent back to the user. There's so many more tags that we could discuss, but unfortunately we don't have the time for this. So let's focus on a set of miscellaneous tags that might come in handy for you. Let's start off with the exban one. Exban is a tag that shows you that a ban is executed. A ban is a way to invalidate the cache. Varnish offers you ways to not wait until an object is expired, but to intervene and to remove an item from cache based on an expression, a regular expression-based system, which we call banning. So when that happens, and when you call something that was marked on the ban list, the exban tag will be added to the Varnishlog output. And exban says that it is a banned lookup. So when you look up something in cache and it was marked on the ban list, it will remove it from cache, and instead of hitting it from cache, it will bypass the cache, go to the backend, fetch the data, and return it, and store the most recent update of the data. When a miss occurs in Varnish, you expect that the corresponding backend response will store the output back in cache for the next request, so that one will be a hit. But that's not always the case, because in the backend response logic, Varnish could still decide to not cache the output for a variety of reasons. So it will be stored in a sort of negative cache that we call the hit for pass cache. And by default, it's stored there for the next 2 minutes or 120 seconds. If you see hit pass, in your log line, that means that the thing you're trying to get was stored in the hit for pass cache. So that means it won't be queued through the decision-making process, but will immediately be sent to the backend. And the response will not be cached, but will be sent to the end user. And you can see that in the next example. We're trying to address the footer, but the footer response is stored in a negative cache. So the payload isn't really cached there, but it is marked that footer shouldn't be served from cache for the next X amount of seconds. And that's a way you can indicate that. That's important in the decision-making process. If you don't know that, it might seem confusing and you might don't know why an item is not served from cache. In Varnishlog, it's not just about hits and misses and why it was a hit or a miss. If something is stored in cache, you probably want to know how long it is stored in cache and what was the reason and the decision-making process to determine the TTL in the first place. Now, luckily, there's a TTL tag for it, and it's very verbose. It gives you lots of information about the decision-making process. Let's show you how it works. The first column of the TTL tag is either RFC or VCL. When the value is RFC, that means that an RFC-compliant response header was used to determine the TTL. That could either be cache control or expires. When VCL is the value, that means that there was a potential override in your VCL file. If you define the TTL in your VCL file, that value will have the upper hand and will have precedence over potential cache control or expires headers. When there are no expires headers or no cache control headers, there will be a VCL-based default as well. And that's 120 seconds or 2 minutes. The second column is the TTL column, the effective TTL that was selected. The third column is grace mode, and grace mode is extra time added on top of the TTL. That's useful in case your backend is down. So when a backend becomes unhealthy, grace mode will be used. Say, for example, you have 2 minutes of caching in your TTL and your grace mode is set to 3 minutes. That means when your backend is unhealthy, effectively for 5 minutes, you'll serve potentially stale data to the end user. And gives you some leeway to fix your backend. Keep is the equivalent tag for conditional request. Imagine you're doing if modified since or if non-match claims or validations based on either E tags or last modified headers. During that period of time that validation happens, the keep value will be added on top of the TTL. And let's say you have a keep value of 5 minutes and you have a TTL of 1 minute. If that takes so long, that validation process, for that given amount of time, you'll be serving stale content to the end user. The next column is the reference time for TTL, that's just a timestamp, followed by the H header. And the H header signifies the amount of time an object has been stored in cache for. The next 3 tags are only displayed for RFC-based output. These are date, expires, and cache control max age or smax age values. That makes sense because if there was no corresponding RFC-based header, this information would be irrelevant. And it is not displayed when you have VCL-based output. So let's give you an example. Let's show you how it actually works. We see that the first column is VCL, so that means that there was no RFC-based header found or that it was overridden in the VCL file. The TTL is set to 120 seconds. There's 10 seconds of grace mode that was added. There is no keep time, and then there's a reference TTL that was mentioned. Let's switch it up and do an RFC-based example. This example has a 500-second TTL with 10 seconds of grace mode and no keep time. What you see next is 3 identical timestamps. These translate to 1st of August 2017, 14, 47, and 52 seconds. So that means that the reference time has that value, the H header has that value, and the date header has that value. What follows next is 0 for expires, so there was no expires header, but there was, however, a cache control header that either had a max age or an smax age that set the TTL to 500. It's important that you don't set the H header yourself. Varnish will do that for you. If you would happen to set the H, all that time you've added will be deducted from your TTL, which can have a major impact on your caching. And you can see that in the next example, someone added an H header with 3 seconds, and that deducts 3 seconds from your caching. So although you set your TTL to 500 seconds, 3 seconds is pulled off, and you can see that in the timestamp column, the second timestamp column. The next 2 tags you already know. We've mentioned them before, more specifically in the parts about transactions and the relationship between transactions. So we're talking about the begin tag and about the link tag. The begin tag states the start of a transaction, tells you what kind of transaction it is, and if it depends on a parent transaction, it notes the ID of that parent. It also gives you a bit more information about what's currently happening. The link tag, on the other hand, displays subordinate requests that were triggered from this transaction. It gives you the kind of request, it gives you the child ID, and then some more information. The final tag we're going to mention and we're going to look at is the timestamp tag. And that timestamp tag keeps track of internal timing within the transaction flow. It is quite useful to determine how long the execution took and in which part most of the time was consumed. So let's look at the specification of the tag. The first column displays an event label. It displays information about what we're actually measuring in terms of time. Followed by the absolute time of the event. That's the current timestamp. All displayed in Unix timestamps, of course. The next one is the time since the start of the work unit. So that's an incremental counter that displays the total time consumed at this stage. If you want to know the individual time it took to execute that stage, you'll have a look at the last column. So let's see this in action. Let's look at an example. The first thing we're seeing is a request transaction. That is measured through start. It takes 0 seconds, of course, because it's just the start of the transaction. But what follows next doesn't take any time as well. That is receiving the request. What does take the majority of our time is the fetching, which also makes sense, of course. And you can see that in its totality, it took 0.048071 seconds. You can see that the last and the second to last columns are the same. The second to last column just increases as time goes on. We're seeing that we reached the processing stage, which takes a couple of milliseconds. And finally, we see that returning the response takes 0.000037 seconds, which is virtually nothing. But what is important to note is that the final time, the total time it took to process that request transaction was 0.048125 seconds. Now we want to dig a bit deeper and figure out why the fetching took so long. And for that, we have to have a look at the backend request. And you can see there as well that it starts at 0 seconds. Backend request sending takes 0.000199 seconds, which isn't that much. But what makes total sense, of course, is that retrieving the backend response takes the majority of the time, 0.047725 seconds. Added with a bit of housekeeping code, we end up with that 0.048071 that we saw in the request transaction. So it's very, very clear what consumed most of our time. And if we have concerns about delays, right there, right then, you can see what's currently happening. You've seen it yourself, there are a lot of different kinds of tags, and all these tags appear in your logging output as you run Varnishlog unfiltered. This can get messy real quickly, especially on busy production systems. So that's why you need to filter those tags and reduce the size of your output. And we can do this by using -i, and we've seen that before in a previous example. You can use -i to filter out the tags you're interested in. But that's not the only way. In this chapter of the video, we're going to go over the 4 different kinds of tag-based filters. Number 1, -i, as stated before, include tags. -i uppercase, very similar, include tags, but based on a regular expression match. You have -x, and that's the inverse, it's excluding tags. And you have -x uppercase that does the very same thing, exclude tags based on a regular expression match. Example time. Let's filter based on tags that we want to include. And let's do a very useful example. The next command you're about to see is one I use quite often myself because it's the most essential form to figure out what URL was called and what flow it passes through. So we're doing varnishlog -i rec URL and then followed by a list of tags we're interested in. In this case, VCL call and VCL return to see some VCL behavior. And we're grouping it by session, and here's the output. Not really a big surprise, I guess. You see the request coming in for the homepage. You see the flow, receive, hash, lookup, hit, deliver, so it was a hit. You see another request that's incoming, that's /header, that's an ESI call that results from the request. You can see that it's indented with 3 asterisks. That was a hit itself. Similar deal for the navigation, which was also an ESI call. Then you have your backend fetches for all the different bits and pieces, and it comes out quite nicely. That is the most essential way of filtering log output. There's even a shorthand because interestingly enough, you can do -i and mention a tag you're interested in, and you can repeat that, -i tag. But you can also create a list, -i, and then the different kinds of tags, comma separated. But these comma separated values also support globs, so you can add a wildcard. So to shorten this down, here's the example. varnishlog -i rec URL, comma, VCL underscore asterisk. Okay, let's continue. Let's exclude some tags. So what we're going to do is we're going to import the entire request context, -i rec asterisk, but there's a couple of headers we're not really interested in. So we can use -x to exclude those. Check out this example. Varnishlog -i rec asterisk to include all request-based tags. And then we're just going to exclude the request headers and the part where we unset request information. And then you'll see the output. You have the rec start, rec method, rec URL, rec protocol, and rec ACCT. So that's basically what you're getting. It's an ideal way to combine includes and excludes and include everything from a specific context and then exclude the bits and pieces you don't care about. Tag inclusion and exclusion often gets the job done, but sometimes you need more subtleties. Imagine you have a situation where you want to include request headers, but not all of them, only specific ones. To do that, you need regular expressions. And you can use -i uppercase to include by regular expression and -x uppercase to exclude by regular expression. The following example will show you how it works. So what we're doing here is -i rec header colon accept dash language. And also -i lowercase rec URL. What this does is it includes all the request headers, but only the ones that match accept language as its value. And then next to that, we want to include the request URL. What this displays, as you can see in the output, is for every request the URL and the accept language header value that is associated with it. Similar deal for exclusion. We can include the response headers and the request URLs, but then we want to exclude all the resp headers that start with an X lowercase or uppercase. And these are usually custom response headers. We want to strip out those. And what you see then in the output is the request URL, the response headers, but not the response headers, let's say with the X varnish header. That one is excluded. Let's end this section with an all-in-one example where we use uppercase -i, lowercase -i, uppercase -x, and lowercase -x. Check out this example. What we're doing here is including the response headers and all the rec tags. Next up, we exclude all the response headers that start with an X followed by a dash. We include the timestamp, but only the response timestamp, so only the final timestamp where we can measure the total time it took to execute. We're going to exclude the request protocol, exclude request acquisition, I guess it's called, and we're going to group by request. This is the output we're getting. All the request information, only the response headers. The timestamp with the final timestamp of the response, that took 0.00068 seconds, which was quite fast, and the exclusion of custom response headers that start with X dash, uppercase, and lowercase. Quite powerful stuff, but not yet enough. We need more tools to get the job done. Although we've limited the size of a single transactions, there's still transactions in our output that we don't care about. So we need to filter out the entire transaction rather than specific tags in the transaction. And that's where VSL queries come into play. VSL queries offer a very rich syntax to filter out full transactions from the output. They're similar to tag-based filters as they use the same tags and same values, but they differ because you have multiple operators and you can combine these operators, you can chain them with the typical Boolean logic, and or not. There's ways to do comparisons equal and not equal based on strings or numbers. And you can do numeric comparisons like less than equal, more than equal. You can even match patterns, regular expression patterns that is. Here's the most typical example I could think of, and it's one I use quite often myself. We're including via -i, and what are we including? The request URL, the VCL call, and the VCL return tags. But we don't apply this to all transactions. We only care about the home page. So what we do is we add -q and state request URL has to equal /. And then we get the output for the home page. So in this case, we receive the request for the home page, we hash it, we look it up, and it was a hit, and we return it. The next example is also quite useful. We display URLs for transactions that were either missed from cache, so that means they weren't yet stored in cache, or passed, they were bypassed from the cache. Pretty simple, we only display -i rec URL, and we perform an OR call using a VSL query. We state that the VCL call has to equal miss, or it has to equal pass. Have a look at the following example. It's a command with which we list the URLs of all the requests that took more than a second to load. And as you can see in the VSL query, there's a bit more intricacies to using it. And there's some syntax I haven't explained before. And let me show you the full way you could address tags. The first thing you can do is specify the level. So if we're dealing with sub requests, you can say, hey, I want ESI, so you increase the level. You can say, I want a tag list. You can specify a record that you want to match, and there's even fields you can match. We're running varnishlog -i lowercase rec URL to include the request URL. We add -i uppercase to include timestamps, but only the response timestamp, only the final timestamp. And we query out transactions, and we only want to have the transactions where the response time is more than a second. So that means we're matching the timestamp tag using the response record prefix. And for field number 2, which is the timing, we compare it to 1.0. So it has to be more than 1.0. And then we'll be getting the timing and the URL for requests that took longer than a second. At this point, we've become pretty good at filtering out the output, and we're getting the representation we want by performing tag-based filters and excluding information based on VSL queries. But there's plenty more command line options we can use, and let's go over a list of miscellaneous command line options. If you're running Varnishlog, you're only monitoring the tail end of the memory block that was allocated. But by default, varnished initiates the VSL, the Varnish Shared Memory, with 81 megabytes of memory size. So that means there's plenty of size that is not monitored. So if you want to increase the sample of your monitoring, you can add -d, and it dumps the full contents of the memory on which you can perform filters, both tag-based filters and VSL queries. So if you want more information about a certain assumption you have, -d gives you the full memory dump. If you're running Varnishlog without adding any additional command line options, the logs are considered transient. You can persist them to disk by adding the -w parameter and specifying a path and a file name. If you want to append more than one log to a file, you can add the -a lowercase option. If you want to store it in a human readable format, you can append -uppercase a. But mind you, if you want to replay and read those files, you have to specify -r, and it has to be in binary format. Let's see an all-in-one example. We start off with -i to only filter the tags we're interested in, followed by uppercase D to demonize the process, so will be run in the background. -a lowercase to append to the file system, -a uppercase to write it in a human readable format, and -w to specify the path. In this case, var log varnish custom.log. To be able to figure out what the process status is, we're writing a pit file using the -p uppercase option to var run custom_varnishlog.pit. When you've reached this stage in the video, it means you've gotten the hang of it, and by now you're pretty good at using Varnishlog to your advantage. But mind you, Varnishlog is not the only binary that uses the VSL. There's different binaries that leverage the memory logs, and varnishtop is one of those. Varnishtop has similar behavior, it uses similar syntax to Varnishlog, but the only difference is that the output is incremental. It logs out the X most popular occurrences of a specific log. Here's an example where we only display the request URLs, but the most popular ones. So it will list the most used, most requested URLs. Did you know you could use all the other filtering options as well? Look at this example. Varnishtop -i uppercase rec header accept language -q request URL equals /. What does that mean? We only want to see requests that match the homepage. And for those, we want to see the most popular accept languages. So what do you know with this one? Which languages people use to access your homepage, and it lists the top ones. In this final part of the video, we won't be focusing on operating Varnishlog. We'll focus more on the meaning, focus more on gaining insight, focus more on getting value. Here's a couple of scenarios that you'll probably encounter when you run Varnishlog in production, and where Varnishlog will help you to figure out what's going on. Here we go. Why didn't Varnish cache my object? If you're familiar with the VCL flow, you'll know that Varnish decides whether or not to cache in 2 stages. First of all, upon an incoming request, it will check if it's an idempotent request and if it's a stateless request. Idempotent means it has to be a get or a head. Methods that change the behavior of the response, like put, post, delete, and others, aren't considered cacheable. Next up, stateful or stateless. When a cookie or an authentication header is involved, this implies that user-specific content is used. So that means Varnish will not cache. Of course, you can influence that behavior, and that happens in a lot of cases by writing custom VCL. But if we look at it from an out-of-the-box perspective, this is the behavior you'll get. And this is what Varnishlog will output if you check the VCL call and the VCL return tags combined with meta information you need like request information and response information. Speaking of response information, on the way back, when Varnish considers something cacheable, it fetches it from backend, then it could still decide not to cache and store it in the so-called hit for pass cache. If there's a set cookie, if there's a negative time to live, if there's vary headers on all the headers, then it will decide not to cache. And you'll clearly see that in the VCL call and VCL return headers and the payload you're getting back under the form of the backend response. Let's look for these kinds of requests by issuing the following command. We're including all the request information and all the VCL information. We're excluding the rec start and rec ACCT, but we're filtering out all the VCL calls that equal pass. So that means when a pass was involved, when something was deliberately bypassed to the cache. And you'll get some output like this. The output you're seeing here implies that there was a cookie. So cookie, my cookie equals blah, means, hey, there was a cookie set, we won't be caching by default. And you see that in the behavior, receive, pass, hash, lookup, pass, fetch, deliver. So it's clear here that the cookie is the reason why it's not cached. Here's a second scenario. Same command, and the output we're getting returns a post call. You receive, pass, hash, lookup, pass, fetch, deliver. That's because it was a post call, it's non-idempotent. It implies that changes will happen by issuing that call, so we won't be caching it. Final example of a request that is not cacheable is an authorization header. Same command, different output. We're getting an authorization header with basic authentication, and again the same behavior. Receive, pass, hash, lookup, pass, fetch, deliver. The second reason why Varnish could decide not to cache an object is because the backend response doesn't satisfy certain criteria. Criteria being not being able to cache due to specific cache control or expires headers, or because a cookie was set. Let's run the following command to examine these scenarios. We'll be running Varnishlog, including the request URL, the VCL return, the VCL call, backend response information and the TTL, and we'll only display transactions that have the hit for pass tag in them. We'll group the output by request, and this is the output we're getting. So in this scenario, we're retrieving the my URL resource. It's a receive, it gets hashed, so that means in theory the request is cacheable, but on lookup it gets passed to the backend. When we look at the backend request, we're noticing that the cache control value is set to 0. So cache control max H is 0. Also in the TTL tag, we're noticing that RFC 0 is set. So that effectively means that it is not cached. When you will perform the next request, you'll notice a hit pass tag right there in the request. There's also a secondary reason, namely that cookies were set, and the following output shows you just that based on that original command we've executed. Similar scenario here, incoming request that seems cacheable in theory, but we get redirected to the pass logic. When we look at the backend response header, cache control header seems fine, but we're getting a set cookie. Set cookies indicate a state change, so that is stored in the hit for pass cache, in the negative cache. And that's not necessarily a bad thing, because if we change the state, you don't want to be caching that. So that's regular behavior, but still we're able to identify that. In summary, tools like Varnishlog and varnishtop can help you optimize the performance and the hit rate of your Varnish instance. As an admin, you'll use them to your advantage, and it will give you the insight on objects that are present, such as request, response, backend request, backend response, and objects, but also transitional information, VCL call, VCL return, all these tags you've seen. Use them wisely and make sure you can increase the performance or decrease false positives. I've also written a book about Varnish. It's called Getting Started with Varnish Cache. It is published by O'Reilly. Check it out here. There's a link right there, and there's plenty more information and plenty more blog posts about Varnish coming on this very channel. Thank you for checking it out, and see you next time.